Software Engineering Daily is sponsored by Hired.com. If you're looking for a job, Hired.com is the place to start. I've used it personally and it is an excellent service. Software engineers and designers can get 5 interviews in a week with top companies. Go to hired.com/softwareengineeringdaily for a $4,000 bonus upon accepting a job. Thank you, Hired.com. Jonathan Dinu and Ryan Orban are the co-founders of Zipfian Academy, which trains data scientists, engineers, and analysts. Jonathan and Ryan, welcome to Software Engineering Daily.
Hey, Jeff.
Thanks, Jeff.
So what is Zipfian Academy?
Yeah, so Zipfian Academy all started from some idea that me and Ryan had early on when we started getting much more into data. And I'll let Ryan talk about kind of his path to it, but originally, it came about trying to just educate and spread some of this knowledge that used to live in big tech companies. It was kind of siloed away. Not many people talked about it. There weren't books and resources. So it started off to teach. It grew into this immersive 12-week data science bootcamp covering Python, software engineering, data engineering, machine learning, statistics, kind of the whole breadth of what you might need as a data scientist. And the key thing that I think we really wanted was to focus a lot on placements and outcomes, because we both are kind of graduates of traditional higher education. And from day one, we wanted to make sure that if people come through our program, they can have the skills to be a data scientist in industry, and also can go through the whole process of interviewing and get landed in a job.
Sure. Ryan, I guess we'll hopefully get to your background throughout the show, but I did want to ask you about a talk that you gave where you described data science from the perspective of a company that's recruiting people. And you described data science as this thing that often gets conflated between all these different roles. Like you find, people will be looking for something that is like a software engineer and a data engineer and a statistician and a data scientist. And companies seem to often not really know what they're looking for with a data scientist. Would you say that's accurate?
Absolutely. We have talked to hundreds of hiring managers and data science managers kind of throughout the industry, both in the Bay Area and nationally. And, if you went and asked each one of them to define data science, you would get 100 different answers. Data science as a field is relatively new. It's a few years old. A lot of people will say that data science has been around forever and that it's just, statistical inference. But really what we're seeing is a confluence of all these different skills, both computer science, machine learning, statistics, and software engineering as applied to industry problems. And when you look throughout the industry, everyone are using these components in different ways. And so one of the struggles that we had early on in our program, which we kind of think of as the last mile, it's for professionals and academics who have a lot of previous experience, but really need some additional training in the practical side, right? The actual applications and the ability to use a modern tool set to solve some of these problems is creating a foundation that is applicable to an entire industry. And that was one of the hardest components because, you talk to all these different companies and they all have different needs. And so one of the things that we did when we started is going out and we talked to a lot of the eminent data scientists in the field and really took almost a joint operation. We said, what are the things that are common and what are the things that every data scientist needs to learn? And we don't tell people that you're going to come out of this program being an expert data scientist, that you're going to have to be on your own path, right? And that is determined by which company you go for, what industry you end up in. You're going to continue along that journey, and we really see ourselves as an accelerator to get you there. And so we spend a lot of our time kind of counseling companies in hiring data scientists, both figuring out their needs and where we can create the most acceleration within their business. And one of the things that we always tell companies is that instead of looking for that unicorn data scientist who can do it all, right? Someone who's going to come in and revolutionize your entire company and your data backend and going to generate amazing insights and be a fantastic communicator all at the same time. Those people do exist, but they're incredibly well compensated. They're in very high demand, and they only want to work at the most interesting problems. And so we always tell our hiring partners that they should look to assemble teams of data scientists, teams of T-shaped people that have complementary skill sets that are going to be able to work together to solve problems and communicate the solutions to the rest of the team.
What is a T-shaped person?
Yeah, a T-shaped person is someone who's a broad generalist, right? So they have kind of some surface level skills in a variety of different things, maybe software engineering and machine learning and statistics and communication and kind of business acumen, but have a deep domain level expertise in one field. So you might construct a team where there's a statistics expert, a machine learning expert, someone who is an amazing software engineer, and maybe someone who's really attached and understands the business goals and is able to communicate the findings of that team, to a CEO and our executive. And they can all work together to attack the problem using those generalized skills to work together and have that common language and common knowledge, but are really contributing their own deep level expertise onto that team that is going to create something that is better or greater than the sum of its parts.
Jonathan, what kinds of students do you see joining Zipfian Academy? Like, what is the experience level when somebody comes into Zipfian, and what are they looking to achieve?
Jeff, I'm actually going to jump in there real quick because one component that you probably might not have heard is so Zipfian Academy actually joined Galvanize in November of last year.
Yes.
Yeah, so we're actually part of Galvanize now, so we should probably refer to the program going forward under the Galvanize
absolutely.
moniker, not
of
Zipfian.
Course.
Yeah.
Of course. No, we will discuss that later. No, I knew that. I didn't know to what degree the branding was at. But okay, so Galvanize.
So whatever you call the name, we usually see students and applicants fall into one of three buckets. So I think the most typical, or what most people think of as people transitioning into data scientists, are these post-academics. So it's people who have either been doing research as a postdoc, working as a professor, or even in the middle of a PhD program where they really like the numerical, quantitative aspect of things, but they realize that professional research or being a tenured professor isn't for them. So they're looking for something that would be intellectually stimulating, but can leverage kind of all the quantitative knowledge. So post-academic would probably be the most obvious transition. The other one is your typical developer or software engineer who might want to solve some more interesting and creative problems. So they've been a software engineer in industry for 2, 3, 10 years. They've been programming web applications or kind of software architectures, and they really want to think more critically about some problems and analysis. And the third group that usually applies is pretty interesting because it has some of the most breadth in backgrounds. And these are people transitioning from industry who might be working at companies that use data, but they may not be on a technical or data team. So these are people who are consultants, project managers, people who have been working with engineering teams and really want to skill up because they know the domain, they know the problems that they can solve, and they just need the technical and theoretical backing. So each one of those, if you think of this T-shaped person, is missing a little bit of the T. So most people who apply have some experience. No one comes in with zero programming experience and zero technical experience, but usually they need to fill in some certain aspects.
Okay, interesting. So let's get into a discussion of the curriculum. When these students all start, what are the first types of tasks or exercises or technologies that they're presented with? What does the beginning of the curriculum look like?
Yeah. So the first week is really focused on just software engineering and programming to get everyone to a certain baseline with the engineering side of things, no matter where they're coming from. So we start them off on day one with a very hands-on applied problem where they're using Python. Most people coming in already have experience with Python. We require it in our interview process. And we also have a fairly extensive pre-course curriculum. So before people even step into the classroom, they've been working with the tools, the libraries, and day one is really to test them to make sure that they're all starting from a good baseline, and also just hammer in some best practices. So they go from working with Python and files and just parsing data to using some of the more advanced libraries like pandas to do some more exploratory data analysis, and also cover a few just basic computer science things that would be helpful going forward, such as object-oriented programming and software design, as well as just how to learn as a programmer and use things like Google Stack Overflow, read the documentation, understand what a stack trace is, which is something that I think everyone who's experienced takes for granted. Is my program's breaking, how do I know what's going wrong? And usually that's something that you just get through years of banging your head against the wall, but we really want to set all the students up for success. So by the end of the first week, everyone's at a relatively stable baseline in terms of programming ability and software. So the rest of the curriculum can really focus on some of the more advanced analytics and case studies.
So advanced analytics and case studies. So when I went through my computer science education, most of the classes were like a series of projects interspersed with tests. How does Galvanize compare to that format? Like, what is the curriculum for the remainder of the academy look like?
Yeah, so the curriculum as a whole, we really, when we set out to plan it, again, we're focused on what do we know people need to be able to do to actually be practitioners? And let's backtrack from there. So we start with the end in mind of these are the common problems people are solving in industry. Things like churn prediction, working with user metrics, doing natural language processing, being able to perform some predictive analytics. And then we backtrack from there and say, what are the techniques and theory that they would need to know? And let's fit that into the remaining 7 weeks. So just the high level, it's a 12-week program. The first 8 weeks are formal structured curriculum where students pair program, they work through exercises, and the latter weeks are focused on a project and interview preparation. So for the remainder 7 weeks of that structured curriculum, students start off with some statistics and probability fundamentals, but it's all taught through this lens of what do data scientists need to do in industry and how do they work? So even when we're doing statistical theory, it's all grounded in how can we apply this and what problems do people use this to solve and how do they solve it? They solve it together, they solve it on teams. So let's have everyone pair program, let's have everyone talk and collaborate together rather than having it be these projects that you can't talk to anyone or a test where you're grilled on how quickly you can learn something and pass a test in an hour. So there are assessments just to give this grounding to make sure that the students understand the material from our perspective, but also to let the students know a little bit of a self-assessment of how do you stack up to what we expect. So assessments throughout, and then most of the exercises are these hands-on projects. So it's almost all projects, a few assessments, and then lecture and theory thrown in there where necessary.
Yeah, one of the interesting things that you just touched on is this notion of collaboration, and all the coding bootcamps I talk to really emphasize this collaborative aspect, which is very similar to how actual jobs work. I mean, you throughout the day you're talking to your coworkers, you're asking them for help. Of course, you're Googling stuff also, so it's nice to hear that you guys have some sort of Googling and Stack Overflow lessons, because those could be like underappreciated skills. So you mentioned some of these projects. Can you give an example of a type of project that you would have somebody working on?
Yeah. So one of my favorites from the curriculum is basically building this end-to-end prediction system. So we actually set up our own server that fires off data, and the students have to build this web application to build an API to accept new data coming in, to collect historical data, which they then train a machine learning model on. And in the end, when new data comes through their API, they need to give predictions. And the whole model is based around this idea of detecting fraud on the application. And it's general enough that fraud detection can be applied to financial systems, to text and posting, things like Craigslist. You imagine looking at emails and things, you can say that's a fraud or a scam. So we have some data set of a bunch of text, a bunch of fraud, and students build a model and actually give predictions. And if they're really ambitious, they build a dashboard so you can see what those predictions are. And that's something that I think really helps the students synthesize all these pieces together, because data science, very, very much like web development and software engineering, is very interdisciplinary. So the hardest thing that we see with students is being able to make these connections between disparate pieces of the theory and application that we teach, and be able to look at a problem and say, oh, that's a fraud prediction problem. That's a natural language processing problem. That's a optimizing our user metrics and giving recommendations problem.
What are the aspects of machine learning that students have trouble with?
I would say the thing I see that most common is not necessarily the math, the theory, the linear algebra, but it's being able to turn some not well-defined problem into something that's more structured and they can actually apply an algorithm to. And the canonical case is often text. Is I know how an algorithm works with numbers, with a matrix of maybe floating point numbers that represent something, but how do I go from unstructured text, like a news article, into a structured row and column representation with numbers? And that feature engineering or processing of text is often the hardest part. And through it, you usually learn which model to apply. And I hear time and time again, students often at the end of the program just want some guide or some like cheat sheet of just which model do I use in which case. And a lot of times you really need to know your data. You really need to understand the limits of the models, but also the nuances of your data. And that's something that there's not a prescription for. There's some heuristics you can use to guide your analysis on when to use which model when, but the hardest part is things that you just learn through experience of this random forest totally is going to break down on this problem because it has similar characteristics to another problem that I tried it on and it totally failed. So knowing when to use this kind of arsenal of models and techniques and which one would perform best.
Yeah, I would say it comes down to, intuition and knowing how to answer or ask the right question, right? So when you're kind of given a problem, a lot of it can be very vague, and you have to really dig in and understand the data and then be able to have the intuition to know what algorithm to apply. And also, even before applying an algorithm, that what is the question that I'm asking here and what am I trying to solve? And that, we spend a lot of time within the program, but that takes months or years to really get down, and that just comes from experience and actually doing the stuff in practice. So,
Ryan, maybe you would have a good answer to this, given your that presentation on teams, on how data science teams integrate with other teams. We did a show with Greg Lamp, who works at a company called YHat, and it's a company that's working to bridge this rift that forms between data science and engineering teams. And what he said was that what often happens is like data scientists will build these models, and the models will be written in like R or Python, and then they'll kind of throw these models over the wall to engineering teams and say, hey, go implement this in your production code. And so there's this problem, and there's other problems that develop between data scientists and engineers. How do you teach students to bridge the gap between building models and deploying their production code?
I think that's a great question. One of the things that we really believe, especially when we're building the program, is that a good data scientist also has to be a good software engineer. And you see a lot of companies struggling to hire and find qualified talent because they're finding people who have the right stats and maybe machine learning background, but they don't have the right software engineering expertise to work with their engineering team to put this stuff into production. So we do a few things in the program. One, which is some of the lessons that John mentioned, was that we actually stress deployment, and we make our students actually deploy their models into production for their project. And we do that throughout the program, and they're always consistently doing that. Secondly is, we have the, I would say, fortune of having a ton of other different programs on our campuses. So we have a full stack web development program. We just launched a data engineering program this month. And we actually foster collaboration between those different disciplines. And so the data science students are working with the data engineering students, are working with the web development students to collaborate and actually build applications that go into production. And one way to solve this, and kind of what I said in my talk, is that we need to have a common language. And so, the more that you can have your engineering team understand just a little bit of data science, and the more that you can have your data science team, learn at least at the first level, some production languages like Java or Scala, the better that they're going to be able to collaborate, and the better that they're able to sit down at the beginning, during, and at the end of a project and potentially find roadblocks and really define milestones that are going to foster that collaboration. And then there are tons of tools. YHAT is amazing. They've come and given lectures to our class many times. They're incorporating our curriculum, as is other companies like Domino and Databricks. And those platforms can do a huge amount of work to kind of foster collaboration between those teams, and being able to view those things, create APIs programmatically. Being able to walk over to a web developer and just give them an API that they can hit. Is very, very powerful. And so we're seeing, not only the, kind of software engineering chops of data scientists, kind of throughout the industry continue to rise, but also these new platforms that are coming out that are really easing that collaboration.
So you mentioned data engineering as being part of the program, or like a separate track, I think. Like, how do you work that into the curriculum? How do you work in big data tools like Hadoop or Spark?
Yeah, so data engineering, we have a 12-week program. We'd love to spend a full 12 weeks on it, which is why we built a separate one that's just for data engineering. But we do about a week of data engineering in the data science program. And really, we start that with a common basis. And so they're going to be doing things like MapReduce and thinking about functional programming in Python. And once they have a handle on that, we can move into Hadoop. And how do you actually do this stuff at scale? We don't go into as much of the administration, but more the actual implementation. So one of the things that we'll do is actually a social network graph analysis using MapReduce. So you can actually import your Facebook friends and do some analysis at scale. And then we move into Spark, which is really up and coming, and we've seen a lot of companies move towards that and look towards Spark as a requirement. And we'll go into not only how it differs from kind of normal, Hadoop, MapReduce, batch processing, but how we can actually leverage stream processing on Spark and use things like Spark SQL. So, we do as much as we can that's applied, and one of the things that we stress is that kind of macro level knowledge of how the big data ecosystem is really put together. And you really see that there's kind of these periodic elements of a data engineering pipeline. And as long as you kind of understand how those pipelines are created and what technologies are available, and have experience at least using one of those. Like I said, every company is going to be different. You can much more rapidly come up to speed on a particular stack if you understand the landscape, rather than if you've just been drilled in a particular tool.
So we're planning to do a week of shows about Spark, and I'm curious, from your perspective, what is the big breakthrough of the technology? What makes Spark so important? How has it changed the landscape?
Yeah, I think when you look at big data tools, versus kind of small, medium data tools. So if you're working with small data and it can kind of fit on your laptop, you're used to using things like R or Python, right? You have an interactive, kind of REPL in which you can, put in, your particular query and get an answer back within, milliseconds. You can do visualization straight on your laptop. You can be much more productive because you're able to have that, kind of sub-second feedback and able to kind of bring to bear all of the tooling, both in the graphical user interface and in the command line. When you move into kind of a big data world, those timelines get really stretched out. If you're working with gigabytes or terabytes or sometimes even petabytes of data, it could be minutes, hours, sometimes even days before you even get a result back. And so when you look at that kind of time to insight, it really slows down that iteration, that feedback loop that a data scientist would want when they're kind of trying to understand or do some exploratory data analysis. And so what's really interesting about Spark is that it's really taken a lot of those components of having it on your laptop and moved it into a big data arena. So things that we could do as far as visualizing things in the browser or getting that real-time feedback, we can now do on much larger data sets using Spark, where if we were using something like Hadoop, we'd have to wait much longer. And so we're seeing that it's very useful for leveraging that kind of quick feedback loop and reducing that time to insight for large data sets, especially in data science.
We'd like to take a moment to thank our sponsor. DigitalOcean offers simple cloud infrastructure for developers. In one click, you can have a mean stack, a Rails application, an Ubuntu box, or another custom environment. Software Engineering Daily is proud to have DigitalOcean as a sponsor because DigitalOcean is the simplest cloud service provider. I've interviewed Moisey Uretsky, who is a founder of DigitalOcean, and he told me that DigitalOcean was based on this realization that other cloud service providers are so complicated. If you want things to be simple when you deploy your application, use DigitalOcean. To try DigitalOcean, go to digitalocean.com and enter promo code SEDaily. That promo code is one word, SEDaily. Now let's get back to our show. Cool. So, why do so many people that are like PhDs in scientific fields like neurobiology or materials science, why do these people end up migrating to the world of data science?
Yeah, I think a big component of it is the PhD to tenure track gap, right? And that there are more PhDs that are coming out than ever before and less tenure track positions available. And so a lot of people are looking for alternatives and an alternative career path outside of academia. And particularly these kind of STEM PhDs, they're already kind of doing data science in a way, in that in order to really be at the height of any field in academia, especially in science and technology, you're going to need to be employing some level of programming, some level of statistical expertise, sometimes some machine learning and predictive analytics, and it might be applied in a scientific context. And so when they look for alternatives, applying what they know and that kind of rigorous insight and being able to take a problem, a research problem, and break it down and work on it over a long period of time, those things map very well to industry. And we've seen a lot of people go through our program and be very successful. The gap becomes, they might be working in MATLAB, they might be working in, some other, kind of system that doesn't map well to industry, or they don't really understand industry best practices like using Git and version control and working in pairs, or even industry terms, the marketing analytics and churn and lifetime value and all these things. So if we can bring them up to speed on those, then they can rely on their own, that domain expertise that we were talking about earlier, to really be successful in industry.
And what kinds of skills does traditional academia generally give these people that need to are deciding to transition to data science? Like, what kinds of skills do they tend to come in with? Obviously, it's varied, but
I think you can kind of put it into a few different buckets. One, specifically those who are going through a PhD program, they have really been trained and kind of pushed in order to kind of ask the right questions, right? They're kind of pushing that envelope of human knowledge, and so they're having to go really deep and think very hard, about a particular problem and come up with something that's novel or new, which I think is really important for a data scientist to understand. The second component is that research element where they are trained to look at a problem for a very long time and to really plan out and to look and exhaust every possibility, which I think is also important. Otherwise, just the core math and science skills, and typically programming is in there as well, is really important. And you tend to find people who are very passionate about their fields and who are going to do very good work. I don't know, John, if you have anything else to add as far as how academia prepares people.
Yeah, I would say it prepares people in good and bad ways. The good ways are what Ryan said, where you do get this very strong curiosity for things, and that really helps because in data science, the hardest problem's often figuring out the question you want to ask. It's not really putting things through a machine learning library and just getting results. It's figuring out which model do I use. So people coming from academia, that's basically what they're trained for, is given some problem that no one knows the answer to, how are you going to find the questions to get an answer? And the flip side of that is the timelines in academia, the kind of workflow, if you will, is pretty much antithetical to what data scientists need to do, where they're basically trained, you have a year or years or 5 years to basically get super deep and super knowledgeable and expert in one specific question, one specific problem. But the nature of the data science industry now is that there's not enough data scientists out there, and every company wants them to do everything. So you have to really focus on how can I be most impactful with the limited time and resources I have. So it's not necessarily get to 100% perfect answer in 2 years, but let's get 80% of the way there in a month, 2 months, 3 months, and then iterate on that and go forward. So a lot of what we've seen in the program with people coming from PhD programs or people who have been researching for 10 years is that it's very hard for them to almost unlearn what they've been doing. And whenever presented with this wide breadth of skills they need to assimilate very quickly, they really want to go down these rabbit holes and learn everything about something like text classification or everything about building a support vector machine. And a lot of times there's diminishing returns to learning so much about one specific model or one specific application, because a lot of times you need to have this general kind of macro sense of the problems you're solving.
Very interesting. So another thing that seems somewhat anathema to how things work in academia is which we've already touched on, is this notion of collaboration and the team structures in corporate organizations or companies. That's not to say that academia is not collaborative, but the way that you collaborate within a company is probably dramatically different than how academia collaborates. How do you teach people that are coming out of academia to collaborate with each other?
Yeah, a lot of it. I guess one part of it is just forced through pair programming, but the more kind of deeper philosophical approach to collaboration happens through a lot of just the structure of our classroom and how we organize the program. It's all these things that people don't consider as part of the curriculum when they think, what's the curriculum of Galvanize Data Science? It's, we teach statistics, machine learning, programming. But I really see educational programs as much more than just the content you teach. And I think the content's actually probably the least important. It's how you teach it and the structure of your exercises, your classroom, your teaching pedagogy. And a lot of the collaboration, especially for people coming from academia, we try to instill through how we organize our days. From in the mornings, we have people work on little mini quizzes, but also just to start discussion around what they did previously. So they come in, they work on a problem maybe alone, but then after it, when they're in between exercises and lectures, they all have this kind of common problem to talk about how they solved it and how someone else might have solved it, doing mini code review type things. And then they work on exercises together. They collaborate on certain parts of projects together. They may not all be solving one similar project, but they might have inputs on given aspects. If I know someone's doing something with images, and in a previous life I did a lot of signal processing and image analysis, I might be able to contribute some knowledge and help there. And they might help me if I'm solving some problem that has a lot of engineering that I don't know about. So it's this forum for people to be able to communicate and collaborate openly, all in a physical space, and having exercises that basically promote people to share answers and not have really, like in academia, first author publications drive things, or not have grades drive things, but have the learning drive things. So everyone's there to learn as much as they can and help everyone else learn as much as they might be able to. And that's something that I think hopefully is breaking down this barrier of everyone's their own island. Maybe they collaborate on these small parts where they come together for a short time and they go apart. It's more about these longer lasting relationships where even on our alumni group, people say, hey, I just started working on a new problem. Has anyone worked on this before? And there's dozens of responses of, oh, I solved this a few months ago at my company. Like, here's what I did. So that kind of ethos, I think, goes a lot farther than any sort of formal type of workflow or agile process or whatever you want to call it. It's just informal collaboration, communication, and community.
Absolutely. So Ryan, I'd love to pick your brain a little more about these different data science team structures that you've noticed in the wild. There's a really good presentation that we'll put in the show notes where you talked about how data science is organized differently at places like Tesla and Google and other companies. What are the trade-offs between these different data science team structures, and how do they work?
Yeah, absolutely. So, what we've seen in industry is, there's more, but the three kind of themes that we've identified are around how teams are structured within an organization. And this is really only applicable if you have kind of many data scientists within an org. As a data science manager, you have to make a decision for, how is my team going to operate? And those three are kind of centralized, we see distributed, and then we see a hub and spoke model. So centralized is typically the most common, and really that's where all of the data scientists are sitting in one room, and they act as almost like an internal consultancy, right? So they're the ivory tower. If you want, some data science time to solve a particular problem, you have to go and ask them to work on your particular problem, and then they will kind of collaboratively solve that. And that has some pros in that you have this really strong data science culture, and that they can collaboratively, solve and tackle problems together. But the con of that is that what can happen if left unchecked is that they lose sight of the business problems that you're trying to solve. And the ultimate goal of data scientists is to deliver business value. And if the data science team is working on things that are interesting to them, like Jonathan was saying, going really deep in a problem that might be intellectually engaging, but does not actually deliver value to the business, that data science team is going to get wiped out fairly quickly, right? Because they're very expensive. And so what people have done to try to get around that is this distributed model, where we kind of push each data scientist into a business unit. So you could say there's one on the marketing team, there might be one on product, maybe one on HR or something like that, and they are basically embedded completely within that team, and their goals are dictated by that team, and they really understand the struggles that the team is going through and the business needs that need to get solved, and that works really well for delivering value and getting a lot of value out of your data scientists. But the problem is they can get a little too distributed in that you don't have that sense of camaraderie. They're not necessarily working together. You typically find them kind of reaching across the aisle and trying to work on each other. And you can actually be solving, the same problem in different teams and not necessarily know about it. And so the kind of mix between those two is something called hub and spoke, where the data scientists sit together and they maybe meet once a week, to kind of collaborate on problems. But they're all assigned to different teams within the organization. And so, their main focus is solving business problems for that team and really understanding, what the needs are. But then they come together and work on those things collaboratively. And so you kind of have this trade-off where you're getting the best of both worlds, where you're getting the requirements from the team. You're getting, at least one or two people who really understand, what needs to be done there. But you're also getting that, kind of centralized control where you can, potentially identify, far-reaching problems within the organization or opportunities across different teams, because you have both, the deep-level knowledge, but also the general knowledge of what's going on throughout the organization. So I always encourage people, if you're a large enough company and you have data, enough data scientists to really explore the hub and spoke model, because I really do think it's the best of both worlds.
Very interesting. Jonathan, I saw a quote from you where you said, you can learn from your students just as much as they can learn from you. And I definitely agree with that. What are the most important things that you've learned from your students?
Yeah, I guess from a higher philosophical level, the thing I've learned is not necessarily assume nothing, but be empathetic to the problem you're working on and the people you're working with. So I think empathy can be an overused, abused word, but from a technical perspective, I think I've seen students approach problems, and especially for their projects, they say, what am I actually solving and why am I solving it? And that's something that I think I never really fully internalized until I worked with 50, 100 students on all their projects. So getting to see that wide breadth and how they approach problems and what they want to solve and why they want to solve it, I think that put things in perspective a lot for me, because I've approached it kind of data science from the lens that I think everyone else comes to it from, either working in industry and solving some very particular problems and not really seeing the forest for the trees, or from a lot of hobbyist perspectives where they get some data set, they're interested in finding out some, let's say, like who the most valuable player on a sports team is based on their statistics. That might be something that you're curious about solving, but then at the end of the day, you have to think, is this hopefully gonna impact anyone, or could it be used for anything greater? And I think the projects in the program are a period where students ask me questions about things that aren't in the curriculum that I've never thought about, and question me and the things that we've taught of, can this be solved, and can I use the things I've learned to actually solve it? So it's kind of this two-pronged learning. One is just learning how to approach problems and people and almost communicate much, much better. And the second component is just on a pure technical level is the students often ask the best questions about when things break and when things go wrong. And that's something that I think a student's the best person to highlight. Is it's almost when you give a new toy to a kid and they try to break it in every possible way and tear it apart. Students in the data science program tend to do that for any new theory or application. If we drop in, here's how to build APIs with Flask, and they say, oh, well, if I can do that with this one exercise, maybe I can build my whole website, or maybe I can build a recommendation engine that gives this real-time feedback. And John, is it possible to do it in this way as opposed to that way? And what happens if X, Y, and Z comes into my data? And those what ifs, I think, really help you understand what you're talking about much, much more and at a much more intimate level.
Yeah, that makes a lot of sense. So Ryan, you mentioned in a talk that you've trained professional poker players at Zipfian. People who are deciding to move from poker to to other fields, as I understand. And I used to play poker professionally back in the boom.
Oh, really?
So,
That's
yeah,
great.
yeah. So this is interesting to me. What are the overlaps that you notice between poker players and data scientists?
Yeah, it's been really interesting. We've had a number of poker players across different cohorts go through, and they've all been really successful. And I think before I kind of get to why, I think it kind of underlies the point, which is that you don't need a PhD to do data science. And that's, something that you see out there, and a lot of people are afraid to even try to get into data science because they don't have, what they think is the necessary academic credentials. It definitely doesn't hurt, but, as we've seen, we have a three-way split between bachelors and masters and PhDs in our class, and they've all done equally well. And so don't let, not having a PhD, kind of hold you back, because we've seen baristas, we've seen poker players go through and do really, really well. And the poker player is really interesting to me because, I think people who get drawn to poker, are the people who have that kind of analytical mindset, right? They want to take a bit of a risk. They want to try to game the system a little bit, right? They enjoy the game theory. They enjoy the analytics. And the people who are at the top of their game, they're thinking about, the analysis. They're thinking about, what are the probabilities of winning and losing this hand. They're sometimes playing, 20 or 30 games or hands at a time. They're typically, scraping data and trying to look at their competition. And so it kind of engenders a lot of the same type of thinking that you would apply to, a data science problem or a business problem, in that, how can I get an advantage, or how can I leverage, data and numbers and probability in order to, kind of beat the house, if you will. And so I think that's why so many people have gone through it, because, the boom has busted a little bit. They're, typically open to a bit of risk and open to, coming and doing a 3-month boot camp and really seem to fall in really well with these teams. And because they can really understand what the problems are and, are creative in their solutions.
Yeah, why have they moved away? When you talk to them, how bad do they say the bust has gotten?
I think in talking to them, they made a lot of money in the heyday. And, with the changing, regulatory structure, especially here in the United States, it's become harder and harder to get your money out. And so I think, there's still a lot of money to be had if that's what you want to do all day. But it's been harder and harder for them to, get their money into a United States bank account. And so they're saying it's kind of just not worth it for them anymore. And I think the other component is to really be successful in poker, unless you're in the World Series, is it's a grind, right? It can take 6, 8, 12 hours a day of just constantly playing. And I think that gets old, especially after a few years. I'd love to hear kind of why you left and how you got on your path that you are now.
Well, I mean, I kind of had an existential crisis when I was like 18 or 19. I had made a good amount of money, and I was like, this is a terrible way to spend my life. And it's one of these things where, like, you find something that you can work really hard at and then make a lot of money, and you sort of figure, I'll figure out later on down the line how to convert that money into happiness. But eventually you get to a point where, like, you've got the money, and the happiness conversion function doesn't, like, magically appear, and so it becomes really worrisome. That's what happened to me, and then I was just like, then I quit the game. Well, I mean, I lost a lot of money before that happened, but it's a longer story, and then gradual movement towards computer science, which I found more fulfilling. So
absolutely.
I mean, yeah. Do you when you talk to them, do they say that they find data science more fulfilling? I mean, one of the interesting things about poker is it's like totally solitary, and like
right.
I would imagine that would be even more difficult to move towards a collaborative data science field than from academia.
Yeah, it's interesting. I mean, I only have a few data points, and they're all anecdotal. But the poker players that have come through are actually very social. They're very extroverted, right? They want to be around people, and that was something that grated on them was the solitary nature of the work. And so they were actually very very excited. And as they've been on an industry, they are very fulfilled, right? This is kind of some of them have gone back and said, I didn't even believe I could be this happy. I didn't know that there was, I didn't know that this was even out there, right? And thank you for accepting me in this program and taking a chance on me.
Oh yeah,
because this is the best decision I ever made. And so a lot of them are and I think that's why data science is so interesting, because it's such a big field. Like you look at machine learning or statistics, and like you could spend your entire life studying this and never understand it all. And never get through the entire statistics canon. And there are always new things that are being invented, new ways to apply this stuff. And so, for me as a lifelong learner, this is the most exciting time to be alive, because, if you are interested in this and you kind of get into the data science position, you could be on a career trajectory for the next 20 years and never get bored. And I think that's the most exciting thing for me, as people are coming in and as this industry continues to evolve.
So I'd like to talk some about the future of data science as we close off. One of the interesting things about data science is that certainly, like as you said, the current state of affairs is like, if you want to be a good data scientist, you kind of have to be a decent software engineer. I mean, in some sense that's not true, but in many senses it is. But there are all these like higher level tools. You've got things like Tableau or Excel. Or even like YHAT. YHAT is kind of moving towards the direction of like decoupling the programming from the access of the API endpoint. And I mean, so data science is certainly like a growing field. So my question is sort of like, is there going to be this gradual movement of jobs opening up for highly technical people that aren't necessarily programmer types? Like I'm thinking like the data-driven marketer or the data-driven social media manager or the data-driven advertising person. How does this fit into the future of data science?
Yeah, I'll jump in here. I know Jonathan has a great answer to this as well. For me, I think, there is this proliferation of data science collaboration platforms and kind of machine learning platforms, and I think that's all great. And really what the short-term focus is increasing the productivity of the data scientist, right? There are a lot of things that are kind of either rote or boilerplates and things that are done over and over again. The less that we can do that janitorial work, the more productive that we can be, right? I think that's great. I think the next phase of that is pushing a lot of these tools down into kind of less technical positions, like you're saying, the data-driven marketer, the data-driven product manager, things like that. And we already have a lot of data, and we already have a lot of these dashboards and things like that. But what I always caution people is, a lot of them say that you are not going to need a data scientist anymore once we come out with our platform, right? And I think that is fundamentally untrue. I think we will become more productive data scientists with these tools, but you still have to have an understanding of the underlying science, the underlying algorithms, and really understand your data, because I see a lot of people learning just enough data science to be dangerous. And they think that, hey, this was statistically significant, or hey, I got an AUC of 0.98. There are a lot of landmines within this field, and knowing where those are and being able to map those out and having the experience to say, this is how we're going to use it here and watch out for this is so important, and is going to be so hard to automate that I still think that the human element is always going to be necessary, but the tools are going to allow us to be more productive and do more than we're able to now with less effort.
So John, what's your vision for the future of data science?
Yeah. So I think Ryan hit the nail on the head on kind of where the toolings are going to go. And this is something that we've seen in a lot of other technical industries. And I like to consider myself something of an amateur historian who looks to the past to kind of almost learn the history of science. And with software engineering and web applications, it wasn't until the 90s and a lot of frameworks got built that people could actually build websites. And now we have graphical drag and drop website builders. But in the 60s, or in the early 80s, if you said, oh, I'm just going to like spend the night, like evening, and like just build a sweet web application, like push it to the internet so everyone can access it, they would think you're kind of a blasphemer. And nowadays, people measure the time to build a web application in minutes or hours. And I think with data science and the tooling, we'll see that, where it's not necessarily data scientists as humans are ever going to go away. We still have people building websites with graphical drag and drop interfaces. It's not that the tool builds itself, it makes it much easier for a human to build what they want. And on the tooling side, I think we're only going to see increases in productivity and collaboration from libraries, tools, platforms. But on the other side of, I think, where the future and where the industry is going is something where I'm seeing a bit of an uptake as of late is just solving more impactful problems through these techniques that typically only engineers and machine learning PhDs knew. And this is where we'll see people be more data-driven marketers. We'll see a lot of industrial applications leverage machine learning to figure out when a jet engine is going to fail or how to optimize a power grid. And all these industries that aren't necessarily considered, I guess, software or digital, I think are adopting a lot of these tools just because they can use them for really like real world impact and gain. And the biggest bottleneck there, I think, always comes down to just education, collaboration, and communication. So you may not need to be a PhD in machine learning, and most people don't need to be one to actually do real data science. But if you do work with someone who's highly technical, building incredibly complex models, they need to be able to communicate how it works and how another non-technical person could leverage it, just as much as the non-technical person needs to communicate, here's the problem we need to solve, here are the constraints, and here's the business value. So you take that and you build a model, and let's work together. So I think the future is going to be bright or dark, depending on education, communication, and I really think openness and open data is really just propagating this much faster than it otherwise would have been spread in the world.
Cool. Well, Ryan and Jonathan, thank you for coming on to Software Engineering Daily and talking about Zipfian Academy, which was acquired by Galvanize. So if you're looking to get a data science education, you can check out Zipfian Academy or Galvanize. I'm not sure where the branding falls at this point, but the quality of the education is still the same or higher. So Ryan and John, thanks for coming on to Software Engineering Daily.
Absolutely. Thank you so much for having us, Jeff. This was great.
Yeah, thanks, Jeff.